Hello, thank you again for watching. I will explain some other clarifications throughout this lecture. This video is going to be talking about hybrid coordinates. This is my third week of of advanced analytical spacecraft mechanics. I'm kind of generalizing like that. I already got my certification, but I should have made a video earlier. But I was kind of reviewing. So this is just explains the general flight mechanics of a spacecraft. Later on, we talk about a NOVA satellite, where how the panel is determined. This gives a mix of discrete coordinates and continuous coordinates, where we can understand different states and different deflections. So let's get into it. This is a bird eye view of a hub and the actual deformation of the panel. This is the angular acceleration initial panel. This is the kind of counterclockwise way of the actual deformation. That's how you probably say it. I provided here a three-dimensional way where this is the satellite hub. Well, this is a three-dimensional way as well, but I'll later get into that. 3D representation is stated here. Over this explains this. I'll go furthermore later on. I need to replace with, okay. We have a three-dimensional hub right here where it's gonna actuate here. It's gonna churn, flex into a 1 degree motion. And when you understand it's gonna have six coordinates, have a 1 degree motion moving, and it's gonna flex. I don't think it's gonna be this extreme, this excited. And other factors can incorporate here. It's gonna be angular acceleration, angular velocity, work, virtual work, forces applied, mass, inertial, and there's a lot of other potential. But once we go more into it, we're going to talk about non-conservative, which I want to mention before. Non-conservative mainly indicating the removal of mechanical energy. So this is the discrete coordinates, the rate with respect to time, or depending on time, as we actual deformation. Respect to time and space. But if it's a lateral oscillation, if it was a lateral oscillation, then there'll be other dependencies here. We need to bring awareness of a general Lagrangian here, as we get lambda equals lambda, which is as we soon spread it out, it's going to be the discrete coordinates t, q dot with q dot. Then we get actually spatial dependencies, and we get on the spatial boundary domain. Here is just the Lagrangian density function here, and the general. It's kind of general, the omega. Here we got slope, acceleration, and spatial and time slope. I think yeah. As we go down here, we mainly convert into the generalized equation to one variable of x. And we get into here, we converge into this dependency on on time. The state's going to be dependent on time. The state's going to be dependent on the points of the boundary. And this is going to be the rest of integral from u to the boundary of L. And as we move into here, the hybrid equations of motion. Here, we're given here the lambda discrete motion. We have kinetic energy depending on the state, which, I mean, in the discrete coordinates we have that, minus the potential energy, q dot. Here, we don't have, here's is the temporal function of here, and we have minus potential function. Potential function is never sorry, oh, my phone's about to die. The spatial function is never depending on time, but it's depending on space. So we just have q, the spatial depending on the boundary, actual deformation, and later on it's going to be defined as the deflection, which is going to be a distributed pressure and distributed force. Right here we have Script lambda represents the generalized coordinates and generalized forces. It is just the rest of it, rest of all the generalized area minus the potential generalized of the space. And if we move here, we have, for convenience sake, we convert this into, for convenience of work, virtual work, non-conservative. The non-conservative means we don't have kinetic energy. This means the generalized forces times the variational of states, discrete coordinates. If we have discrete coordinates, this is an example of F times partial velocity. And the before examples that we did before, and there's other examples further on that you can incorporate, plus the integral of U to L, all this. This represents the distributed, basically if distributed load, if the distributed load, like say, distributed pressure against a wing, airfoil, it deflects it and it moves it around times its the spatial, the variational spatial here times dx respect to x. These are just the other forces that are depending on it. For example, we have its distributed forces, other deflections, other just forces that tend to affect the panel itself, just the others. And as we incorporate here, we need to recall the past equation from Hamilton's principle. It's not Hamilton's principle, Hamilton's law of reaction. Before I talked about that, if you looked at it, which is just variational Lagrangian plus variational work. I need to fix that. It's NC, which is non-conservative, respect to time. 0, as we continue here, we take the integration by parts, make it arbitrary. Here is the complexity here, that's really complex, is that there's other scientists that were getting paid to take integration by parts, integration by parts, integration by parts, and it would tend to be complex. So they converted it into a generalized equation, differential equation. This is a partial differential equation, I assume, yes. And this is the, thank God we're given the answer, not answer. So we take integral of initial time, Lagrangian, and we get these. As we get this, oh wait, sorry. This should have D, all of these discrete coordinates with rates, respect to rates, and this is just the integral with, this should be D. Why did I put D? All this respect to states, this get this versus spatials, and then the spatial time derivative, acceleration, and then the slope, and then the point. And then all this is going to be in respect towards the L. As we take a integration by parts again, we convert it, we get this. And I fixed this. Didn't I fix it? Yeah, we fixed it. We get this long differential equation. And if you look closely into these brackets, you see a pattern here. And if you recall Lagrangian dynamics, we see this, where we get the partial respect to the state minus derivative of the partial respect to the rate dot. And we get the same process here, plus the generalized forces, times the variational states or discrete coordinates, which this will be equal to 0, and we're going to be provided to here. I'll explain it later. Here, on the other hand, is going to be more complex. We're given a little complex situation here, as we're getting spatials and deflections here. And yeah, here's just that stating what's over there. This was luckily given. It's really just taking integration by parts here. It looks really complex, but if you know the rules and the complexities of it, you'll do fine. We need to also note the free. As we know, the variation of Q has to have something times 0, and we just make this whole equation equal to 0, convert this, switch plus, minus, plus, this by itself, so Q equals this plus, it's gonna be this, which is gonna be 0. Convert it, understand the previous, my arm hurts, equation, and as we get dW, no, sorry, this we switch this, I'm getting confused here. We switch this to get that by itself. As we get dQ, we convert that and we switch, because this cancels out. And yeah, yeah, right? I need to review. Oh, wait. Okay, this is the Euler. Lagrangian, wait, no, it's not Euler. What am I talking about? Lagrangian. It's Lagrangian pattern when you make it equal to 0. This time 0 is 0. Okay. Okay, I get that. This I do get, because we're converting as we get variational spatial, we just convert this equal to 0, and we just have this function, internal function, and we just switch these signs, positive, negative, and this as we convert this into the other side, and it's 0, use algebra, we get F, which is the distributive forces, Later on, we're going to be presented a problem where we're not going to have distributive forces. Some other problems, you're going to have distributed pressure, distributed other stuff. So in here, we have an example. This axial rod and spring mass system, there's going to be some things recalled from the previous for axial rod systems and just spring mass systems equations. Like for example here, we have right here, spring mass equation. Here, I think it's transitional or temporal spring mass equation, which, gives, this is a different partial differential equation, and this is just the particle motion equation. So right here we're presented, we need a wall here. I don't know what was going on with me. We need a wall there. Put a wall here. As we put, I'm sorry, I did not go over the boundary condition here. Okay, as we understand over here, I did not review this. The rest over here is just the boundary condition. And as we get this kind of be, and later on can be very mixed match, transferably, I think, versatile or something you call it, where it's not given a viable solution. It's mainly depending on the spatial velocities, the spatials, just mainly the parameters. And oh wait. I have to have a second boundary here. Oh my gosh, I'm stupid. Okay, you're gonna see me write something real quick. So I had to get this other spatial boundary. What it is, it's just this cancels out all this equation itself. So I'm just gonna do this. Parentheses. All it is just really just excuse me. It's dots. Why do I keep forgetting that? Partial forces, distributed forces. There you go. Makes it equal 0. And that's our other boundary condition. You have the two boundary conditions over here. So let's continue back here. So we're first starting with Hamilton's extended principle here. So we get this, A equal to 0. It's non-conservative. Alrighty. So as we look through here, we have we have boundaries. And This is just the difference here between the wall and the spring, not spring. This is our discrete coordinate here, y, our discrete coordinate. And what's given, the prompt that was given was the kinetic energy and potential energy. As we know, we can recall before, I don't think I provided before, was the Hamilton's continuous, Hamilton's principle in a continuous system, which it was provided on generally here, but later on it's going to be, we're going to do this in the second try into hybrid coordinate systems. But it's just really recall a lot of stuff. So the rho is the density over here, kinetic energy, A, involvement, which is just the mass, times the u dot squared. As we take a variation, we know variations. We take the variation, letter here, is just going to be u dot, variation u dot dx. Rho A stays with it, plus the constraints, not constraint, the discrete coordinate, here is my squared. Take the variation of that, we get the same process here, and that's kinetic energy. Still, we keep the integral. Rho A u dot, variational u dot dx plus my dot, the discrete coordinates, and these are spatials. Potential energy here. We have the Young's modulus here, A, u prime squared. The thing is, we're going to have to figure out in the future is we don't want u prime or the variational u prime, because it's going to be very, let me see what percent my phone's on. Oh, it's 5. Give me a second here. I want to plug in my phone real quick while I'm still recording. Shit. Okay, it's charging. Okay, I hope you can see. I'm going to do my best to... Okay, so let me see. As we see here, we have kinetic energy. Let me go back to here. Here, we're going to use quadratic, like just pre-cal algebra stuff, where we take a function, let's say like x plus 2 parentheses squared, like that process. But later on, I'll explain it later on when we go into more complexities here. Then we have the constant here. The K2 is the constant times the discrete coordinate, which is here, the spring constant. The left is all it is just the difference of the boundary and the discrete coordinates. That's really just the difference here of the particle difference. It's just a particle difference, basically. As we take a variational, we understand that. As we do that, we got v times y minus y. Use common algebra, and we just do this, and we get that, and we get our just the same process here. Let's get m dot. It's a variation. All right, let's continue here. Hopefully y'all can see this. Alrighty, we take integration by parts to get the u dot arbitrary, so we can get it to 0, and we can understand the ending point. So we take integration by parts of the kinetic energy, u with the integral plane of u to L, which is the ending boundary, not PA. What am I saying? Rho A. As we take the integration by parts formula was just integral u dv equals uv boundaries minus integral v du. And as we incorporate that in our mind, we understand the process of doing everything now. Later on, this is going to cancel out A in rho. We'll cancel out later on. It's going to be divided. And as we do this, do the same process as it is. We do integration by parts. This is all the complexities of it. Then we take a partial, as we understand the partial, All this is the same process here, same process here. We need to incorporate this law because with Hamilton's principle under partial, I forgot why, but we need to denote this because it's equals 0 because the partial, shoot, I forgot. I'll go over that. Take an integral of parts again. Integral of not u, 0 to L. As we get that, we take integration by parts, find these parts. This is with respect to the point of boundaries. And we get for first the wave function, two equations. We get a wave function of, which is an ordinary differential equation for axial deformations. Axial deformations, basically, it's just a wave function. And A cancels out. That's later on here. We get rho u double dot minus Young's modulus times u double dot equals 0. And we get a partial differential equation for particle motion, as we can recall for past examples, which is just m times u, which is the discrete coordinate, u double dot plus parentheses the spring constant 1 plus the spring constant 2 times the discrete coordinate equals spring constant 1 times the point of boundary. And that's over here. And if we recall this equation, we can take it in another circumstance where we call note the respect to the spatial if we just recall these and we note these were given, we can end up in an equation of this, which is just Young's modulus times A u prime, the point of boundary plus the spring constant 1, point of boundary equals the spring constant times the discrete coordinate. I need to review that. That is kind of a problem because I'm kind of not familiar with that. This, I want to give a general, this is just the satellite, Nova satellite, or Nova. I don't know if it's a satellite or spacecraft. I was like, is it Nova? Like, seems like we're getting a representation of a satellite. So this is the, this is the satellite, this is the hub. The panels regulate to flexes, and these are the hinges, and yeah, this is the generalized what a satellite is. And as we use second try of hybrid coordinates of hyperfunctions, we understand lambda spatial, not spatial, particle. What am I talking about? Lambda script discrete coordinates of 1/2 m times the discrete coordinate of y squared minus 1/2 the constant. This is just the kinetic energy, the temporal, transitional energy, and then the movement energy, rotational energy. No, whoa, sorry. What am I saying? Transitional energy is over here. Where is it? It's over here. This is rotational energy. This is kinetic energy, and this is just, kinetic energy. Whoa. What am I saying? Yeah. Transitional energy, rotational energy, kinetic energy. Yeah. This is confusing me right now. This shows us discrete coordinates, understand right here. Kinetic energy minus the other forces, potential energy, with domain boundary here. And as we understand the script Lagrangian, which is just the Lagrangian here, it's just this, as given. The mathematics can incorporate in the same over here. How do we get that? We just get the kinetic energy and potential energy. and we just incorporated all previous laws to get what we needed. Yeah. Okay, then we understand our given. So this is our generalized forces. We do not have generalized forces, but if we have extra forces, like, I don't know, strain or others, we have it right here. We have our discrete coordinate here, y, like we stated before. We have our partials equal to that. Not partials, spatials, respect to space and time. And we do not have distributed forces. Some distributed forces and examples will be distributed pressure, like I stated before, distributed load. It's just a distributed load, which we don't have it here. And the forces here are add up to 0. If we have extra forces, then we incorporate to that. Here, generalized forces, I forgot that if we had extra forces, we apply into here. But if we have generalized forces, some general, what is some general force? Like gravity and so forth. This is the little things we need to incorporate here. As we go recall the equation over here before. Lagrangian generalized forces equals 0. So we recall the spring axial rod, I think it's axial rod, springs mass system equation. Here we just recall that equation previous before. Understand what we found here, which is variational spatial. And what we got that is our ODE here for axial deformation here. As we understand, we look down here, we understand our boundary conditions to recall our other boundary condition here. And it can be very controversial here. It's not going to be really equal to 0 because the partials might not be respect towards the parameters. So it might not be 0, it might be something else. So as we get over here, like we call over here, this equation. All this is recall of what we found here and what was just supported here. Okay, moving on towards 27 minutes. Oh my gosh. I'm gonna go through this quickly. Hub with Euler-Bernoulli beam. So this is the hub, initial hub. This is the Euler beam, inertial representation here. We have angular acceleration. V is the actual deformation, inertial tip, mass tip. We have our potential energy, kinetic energy,